viewers, welcome to CEC Gurukul lectures. In this lecture, we shall be discussing properties of geometrical isomers. Since geometrical isomers are not mirror images of each other, that is, they are diastereomers, their physical properties are different. That is, like their boiling point will be different, their reactivities will be different, their melting points, densities and solubilities will be different. So, please remember, geometrical isomers are diastereomers. That is, they are not mirror images of each other, so their physical properties will be different and some of their chemical properties will be also different. That is, when we talk of chemical properties, their chemical properties will be different. They will react at a different rate, or the addition of a stereo selective reagent will be different. That is, that we shall be discussing how they will react. That is, how are we going to distinguish between the cis and the trans isomers on the basis of chemical reactions. For that we shall be using potassium permanganate, that is cold dilute potassium permanganate, which is Bayer's reagent, and the second reaction that can be brought about to distinguish between the cis and the trans isomers is by carrying out bromination, that is addition of bromine across the double bond. So, before we take up the chemical differences, that how cis and the trans isomers react differently with certain reagents, let us first discuss the physical properties on basis of which we can distinguish between cis and trans isomers. As I have said that their melting point, boiling point, solubility, dipole moment and many other properties will be different. Let us discuss these one by one. So, if we talk of melting point, then please remember melting point of a trans isomer is generally higher than that of corresponding cis isomer. The reason being, the molecules of trans isomer are more symmetrical and hence fit more closely in the crystal lattice as compared to the molecules of cis isomer. And we know when there is efficient packing of molecules in a solid, in that case the intermolecular forces will be strong. Since trans isomer packs better than cis isomer, in that case the intermolecular forces will be stronger in case of trans isomer. So, if we look into the structure of the cis and the trans isomers of but-2-ene dioic acid, that is malic acid and fumaric acid, then in the cis form what we find is that the two carboxyl groups or the shape of the molecule is U shape, as a result of which this molecule cannot fit closely into crystal lattice in solid. Whereas when we look at the structure of fumaric acid, then fumaric acid has a comparatively straighter shape, as a result of which the two molecules of fumaric acid will fit closely into the solid. So, the poor packing in the cis isomer means that the intermolecular forces are not strong enough. Since the intermolecular forces are not strong enough, so less energy will be needed to melt the molecule, as a result of which cis isomer has lower melting point as compared to trans isomer. Since now, if we consider solubility, we know that the cis isomer is loosely packed. Since it is loosely packed, that means therefore its solubility will also be higher when compared to corresponding trans isomer. This is because the molecules of cis isomer are less tightly held in crystal lattice. This we have already discussed. As a result of this, when we compare the solubilities of both, that is the cis isomer and the trans isomer, we find that cis isomer is, that is 79 grams of cis isomer, that is malic acid, is soluble in 100 ml of the solvent, whereas in case of fumaric acid, the solubility is only 0.7 grams in 100 ml. Of we can take solvent as water also, because both of them are polar in nature, and we know that like dissolves like. Dipole, now we have to see which molecule or which isomer has a higher dipole moment, because boiling point is related to polarity of the molecule. Cis molecules generally have higher dipole moment than their corresponding trans isomers. Reason being, similar groups are attached to the same side of the double bond, and when they are attached to the same side of the double bond, the combined inductive effect is additive, that is, it is synergistic, and this will give higher dipole moment to the cis isomer. So here I have taken the example of cis 1,2-dichloroethene. So what we find in this case, that in cis case, both the halogens are on the same side of the double bond, and we know dipole moment is a vector quantity. It is mu, that is, it is the product of charge into and the direction we have to consider. Now when we look into the cis isomer, both the halogens are exerting a minus I effect, and the product or the consequence is an additive effect, as a result of which this molecule will have higher dipole moment as compared to trans isomer, where these two halogen atoms are attached on the opposite side of the double bond, and their two inductive effects are antagonistic, that is, one halogen is pulling on the one side, the other halogen is pulling the electrons on the other side, as a result of which the net dipole moment will be 0, and this compound will not be polar. This will now, the polarity will have the effect on the boiling point, because boiling point depends on the dipole-dipole interactions, and since dipole-dipole interactions are higher in cis isomer, this isomer will have higher boiling points. But there are certain exceptions also. Supposing we had taken two groups, instead of one halogen we take a methyl group, then in that case the inductive effect of two groups will not be synergistic, because halogen, that is chlorine, exerts a minus I effect, whereas a methyl group will exert a plus I effect. So these two effects are opposite. So the dipole moment in this case of cis isomer will be lower than that of trans isomer, because in trans isomer halogen is exerting a minus I effect, whereas methyl will exert a plus I effect. In this case, the inductive effect is synergistic, and trans isomer will have higher boiling point as compared to the cis isomer, and its boiling point will be higher. So the boiling point and polarity will depend upon the nature of the substituents attached to the double bond. The next point we find is that in general trans isomers are more stable than the corresponding cis isomers. Reason being, in trans isomers bulky groups are far apart on the opposite side of the double bond. For example, if we take that of 2-butene, then what we find that in 2-butene, the two methyl groups in cis isomer are close to each other, as you can see on your screens. And then when these two bulky groups are on the same side, there will be greater steric repulsion between these two groups. And since there will be greater steric repulsion between these groups, they will be less stable as compared to the trans isomer. The next method by which we can measure the stability of the cis and the trans isomers, it can be compared on the basis of heat of hydrogenation and heat of combustion. Generally, cis isomer has greater heats of hydrogenation and combustions when compared to the corresponding trans isomers. And we know that the heat of hydrogenation is, as well as heat of combustion, is inversely proportional to stability. As you can see on your screens, we have carried out the reaction of 2-butene with hydrogen in presence of platinum when hydrogenation takes place. So what is a hydrogenation reaction? Hydrogenation reaction is a reaction in which hydrogen adds across the double bond, and the amount of heat that is liberated during this reaction is known as heat of hydrogenation. When we carry out this reaction, we find that in case of cis isomer, the heat of hydrogenation is minus 115 kilojoules per mole. Whereas when we are discussing here the trans isomer. So what we find in case of trans isomer, when we add hydrogen, the heat of hydrogenation here is 115 kilojoules per mole. Whereas when we carry out the hydrogenation of cis isomer, in which the two bulky groups are on the same side, then in that case heat of hydrogenation is minus 150 kilojoules per mole. That means heat of hydrogenation is greater when we carry out hydrogenation of cis isomer as compared to trans isomer. Now if we compare the two reactions, what we find that in both the reactions the product formed is the same, that is, we are getting butane in both the forms. Second point, one of the reactants, that is hydrogen, is also same. So what is different in both the reactions? The difference is in the structure of the two butenes. One is cis and the other is trans. That means the different amount of heat evolved is related to the different stabilities of the individual butenes. That means trans 2-butene is more stable as compared to cis 2-butene. Now if we compare the heat of combustion of the butenes, then what we find that if we are carrying out the reaction of cis 2-butene with oxygen, we are getting carbon dioxide, water, and some heat is evolved here. The heat that is involved in case of cis isomer is 2712 kilojoules per mole, whereas when we look into the trans isomer, here the heat of combustion is 1707 kilojoules per mole. So that means in case of trans also, where the products formed in both the reactions are same, that is carbon dioxide and water, and the reactant, one of the reactants is same, that is oxygen. So that means here also heat of combustion is dependent on the structure of the two butenes, and in this case 2-butene, that is the cis, is again less stable as compared to trans 2-butene, because in this case the heat of combustion is more. So that means on the basis of the heat of hydrogenation and heat of combustion also we can compare the stabilities of the cis and the trans isomers, and what we find is that since the heat of hydrogenation and combustion is higher for the cis isomer, it is less stable when compared to the trans isomer, that is cis 2-butene is less stable as compared to trans 2-butene. Now, if we want to use some chemical methods for identification of cis and trans isomers, the first reaction that we can do is we can carry out the heating. What is the effect of heat on cis and trans isomers? They will be different. The chemical properties will also, some of the chemical properties will also be different, because cis and trans isomers, they will have similar but not identical chemical properties. What I mean here is that if we carry out the reaction of cis and trans iso 2-butene with Bayer's reagent, that is dilute alkaline KMnO4, then hydroxylation will take place. That is, OH will add across the double bond, but the products formed will be different, because in this case the addition of OH across the double bond is cis, and we will get different products. So these properties, that is the chemical properties in which the cis and trans behave little differently, or they do not have identical chemical properties, can be used to distinguish between the cis and the trans isomers. So let us look into the first reaction, that is, if we look at the effect of action of heat on, supposing we are taking two unsaturated acids, that is malic acid and fumaric acid. In malic acid, the two carboxylic groups are on the same side of the double bond, whereas in fumaric acid, the two COOH groups, the carboxylic groups, are on the opposite side of the double bond. So here we've taken the example of cis-butene dioic acid. So when we look into this example, what we find in this case, that the two carboxylic groups are on the same side of the double bond in malic acid. So therefore, this, when we will heat this molecule, this will form anhydride easily. As you know, that when we want to compare, when we want to convert a monocarboxylic acid into its anhydride, we either heat it at high temperature or we heat it with a dehydrating agent when a water molecule is removed and it is converted into anhydride. Similarly, 1,4-dicarboxylic acids, in this case, we are taking an example of but-2-ene dioic acid, which is the cis isomer. The two carboxylic groups are on the same side of the double bond, so they will easily lose a water molecule, converting into malic anhydride. Similarly, if I take an example of succinic acid, which is 1,4-butane dioic acid, that on heating will also form succinic anhydride, because there also the two COOH groups are close to each other. But if we look into the structure of the trans isomer, that is trans-but-2-ene dioic acid, then what we find, that two carboxylic acids are on the opposite side of the double bond. That is, they are far away from each other. Therefore, when we heat them, they will not form a cyclic anhydride. If we heat them to 160 degrees, they will sublime, but there will be no chemical change. So what is sublimation? Sublimation is when a solid converts into into gas without passing through the liquid phase. Sublimation is when a solid converts into gaseous form without going through the liquid state. So fumaric acid will sublime, whereas malic acid, in which both the carboxylic groups are on the same side of the double bond, will form a cyclic anhydride. So the next method by which we can distinguish between cis and trans isomers is we can carry out the reaction with cold dilute alkaline KMnO4. We know when we carry out the reaction with cold dilute alkaline KMnO4, then in that case addition of OH across the double bond will be cis addition. That is, one of the isomer will give us the mesoform, dihydroxy mesoform, whereas the other will give us the racemic form. These two forms or these reactions I shall be discussing in detail when we discuss chemical properties of alkenes, or rather after discussing the optical isomerism, in which I shall be explaining what are the mesoforms and what do we mean by the racemic form. So what we find is that because of the different orientation of atoms in molecule in space, cis and trans isomers will have different physical properties, that is their melting point, boiling point, polarity, stability will be different, their heat of hydrogenation and heat of combustion will also be different, on the basis of which we can distinguish between the cis and the trans isomers. Now, in this case, till now what we've discussed, as you can see on your screens, the example of fumaric acid in which the two groups attached to the carbon atoms are similar. That means one is hydrogen, the other one is carboxylic group, and similarly to the second carbon also the two groups are carboxylic and the hydrogen. That means when we are considering the geometrical isomerism in these cases, we are looking into the orientation of the two identical groups which are attached to the double bonds. That is, whether the two COH attached to two carbon atoms which are containing the double bond are on the same side of the double bond or they are on the opposite side. Similarly, the two hydrogens which are attached to the two carbons which are containing the double bond, whether they are on the same side of the double bond or they are on the different side. Now, supposing we have a alkene in which all the four groups which are attached to the carbons containing the double bond are different. That is, as you can see on your screens, in this case, one carbon which is containing the double bond is attached to A and B, whereas the second carbon which is attached to the two different groups there are D and E. So that means in this case all the four groups are different. So it becomes very difficult to decide which is the cis isomer or which is the trans isomer. We can decide which is the cis isomer if these two groups were different. Supposing one A was attached to one carbon and the second A was attached to second carbon, and similarly one B was attached to one carbon and the second B was attached to second carbon, then we would have said that the orientation is cis if the two groups are on the same side, and if the two groups are on the opposite side we would have said the orientation is trans. But in this case we have four groups and here we cannot decide the orientation on the basis of cis and trans isomers. For this we shall have to do EZ nomenclature for giving orientation or specifying orientation of alkenes. This we shall be discussing in our next lecture. Thank you.